Good morning, students. So today we will be talking about another topic, viscoelasticity. So we will start the plastic deformation after we have discussed this topic of viscoelasticity. So in the previous lectures, you saw that there is elasticity where you apply a stress and a certain strain, or to be more precise, you apply a load and a certain elongation is obtained in the material. And it is not dependent on time. But some materials, and particularly polymers, show a time-dependent deformation, elastic deformation, which is recoverable. And this phenomena is called viscoelasticity. So this is what we are going to talk about today. Viscoelasticity. So like I mentioned, let me write down some of the important features about viscoelasticity. It is time dependent deformation that is recoverable. And this part is important, the part that it is recoverable. This makes it different from creep phenomena. We'll come to it in a moment. So this phenomena where the time dependent deformation takes place, it is called viscoelastic or inelastic deformation. So when a load is applied, there is instantaneous elastic response, but the deformation in these material keeps on increasing. It does not stop with time. And this continuous change in deformation with time is what is termed as the viscoelastic deformation. There is instantaneous elastic response, but the deformation increases with time. Now, like I mentioned earlier, that this phenomena is different from creep. Why? Because creep is a phenomena which is plastic deformation, which is time-dependent plastic deformation. This viscoelastic or inelastic deformation is usually found in polymers. Actually, it will you can also find it in metals and ceramics, but then it is so small in comparison to the overall strain that it is negligible. And the material where it is most obvious and most important is polymer. That they are ignored. On the other hand, when we are talking about polymers, it is very significant. So in polymers, usually this viscoelastic or inelastic deformation are non-desirable, undesirable. You would see that over time the deformation takes place and the dimension changes and the material does not fit, and these kind of problems can occur. So for example, you may see sagging of wooden beams, denting of vinyl floors, and loss of dimensional stability in some of the components. And these are all basically in examples of viscoelastic deformation, which is undesirable. And as I said, mentioned in the example, this does not happen only in the polymers. It sometimes also happens in non-polymers, and it is non-desirable over there too. But this is one of the primary reasons why polymers are not still used as such a structural material, because this problem of viscoelasticity is what makes them undesirable. Now let's understand this viscoelastic strains with the help of mathematical description. So overall, the deformation that happens can be actually shown with the help of two different components. So one is a spring type component. So you apply a force here, Fe, this is a spring, and the elastic strain, Fe by Ke, where Ke is the spring constant. The other component which defines and which becomes very important with respect to viscoelasticity is a dashpot. So it can be represented as if there is a viscous liquid here and there is a piston. So you apply a force and you can imagine that the piston will not move instantaneously. There will be time dependent phenomena. And here usually it will be the relation is given like this: EV dot, which is the rate of change of deformation or the elongation, which is equal to dEV by dt. This is equal to FB by KV, where KV is the dashpot constant. And if your FV is not a function of time, then we can say that EV is equal to FV times T by KV. Now, these are two extreme examples, and you can say two components which together show the overall behavior of viscoelastic materials. So these are just elements. And don't represent overall response of a viscoelastic material. To properly represent the response of a viscoelastic material, we need to combine these two elements into some combinations, as we'll see, and then that will represent in some of these models, as we'll see, represent some of the viscoelastic behavior of the materials. So we'll be looking only at simple models, and based on these simple models, more complex ones, we know the overall methodology, we can build up more complex models depending upon the requirement. And in this particular course, we will only look through some of the simple models. So first we'll look at a series combination. This is our first simple model, series combination, which is also called as a Maxwell model. So this, as the name suggests, here we are assuming that there is a spring component and there is a dashpot component, which are put together in series. So here the constant is Ke, here the constant is Kv, here the force is being applied. So F is constant in both of these. So F is equal to F1 is equal to F2, and the elastic strain, the overall elastic strain, would be given by EE, the spring component, plus the dashpot component. And this can be, now this EE from based on our previous equation can be written as F by Ke plus F into T by Kv. And therefore what we have is E equal to and this can be represented. So here we are assuming that a force was applied like this. On the x-axis you have force, on the y-axis you have time, and this is t equal to 0. So you are applying. So this is the condition for which we have calculated this. And in response, the material, the strain, as you can see, at t equal to 0, there is some constant value. So let's say this is t equal to 0. So there will be this constant value, and after that it will increase linearly. So this is the response, the extension. This is how the extension in the material will take place. So here we are assuming that sudden force was applied. Another condition where we can evaluate the response of this material is where there is a sudden elongation E. At time t equal to 0. Now, when you apply a sudden in this condition, if you apply a sudden elongation, you know that this one cannot accommodate the strain instantaneously. So all that strain must be accommodated over here, and therefore the force would also be accommodated entirely by the spring. And then gradually, when over time, this force, there will be a force acting on the dashpot, and hence it will slowly take over or accommodate the force. So if we have the strain being completely accommodated by the spring, then we know that F, the initial F that is acting, is equal to K E times E, where E is the total strain that was applied suddenly. And this strain remains constant, but the force that is acting on the spring is now also acting on the dashboard, and this force will now make the dashboard active, or will start to operate. Gradually increasing the strain in the dashpot. So initially there was no strain in the dashpot. Now the dashpot will start to take some of the strains, meaning the strain in the spring will decrease. And therefore the force in the spring will also decrease. And now that at some instantaneous time t, when the force is decreasing, for that instantaneous time, let's say that EE and EV are the strain in the spring and the dashpot, then we know we can write something like this: KE EE, where EE is equal to E minus EV times KE, and F, which is also acting on the dashpot, where we can write KV d EV by dt is equal to E minus EV times KE. Now this equation is in a differential form, and we can write it like dEV by E minus EV equal to KE by KV times dt. Now this term KV by KE can be taken as strain relaxation time, and therefore this term can be written as 1 over tau. So this can be written as dt by tau. And now we can integrate on both sides, and what we get is ln E minus EV by E is equal to minus T by tau. And if we take exponential on both sides, what we get is E minus EV equal to and we also know that E minus EV is equal to F by KE. Basically, this is EE. So we can also write it as F by KE, and F naught, which was the original force, can also be written as in terms of KE and the total strain E. Now, substituting these two over here, what we get, so we can substitute this by E minus EV equal to F by KE. So if you put E minus EV inside this log natural, okay, there was this E term. Now if we put E minus EV equal to F by KE, so on the numerator we have F, on the denominator we have KE times E, and KE times E, which is the total strain, is equal to F naught. So this becomes F by F naught equal to EXP minus T by tau, or in other words, F is equal to F naught EXP minus T by tau. So for the condition where, for this simple looking condition, configuration where we have series combination of spring and dashpot, and we apply a sudden strain. Okay, so if we were to plot it, it would look something like this. So if we are applying sudden strain, so this is like this is T equal to 0, and as a response, the force would change like this. So initially there is a force F naught, which is the force that you see generated because of the spring, but then the dashpot starts to accommodate the strain, and when the dashpot takes the strain, then there is no force generated or resistance force generated by the dashpot, and hence the overall force keeps decreasing, and therefore eventually it will die off to 0. So this is equal to Ke times E. And this gives us, for this particular condition where we have series combination, one, when the sudden force was applied, how the strain changes, and once and in the second condition, when the sudden strain was applied, then how the force changes over time. Now let's look at another simple combination, which is a parallel combination. Which is also called Voigt model. Now, as the name suggests, what we have here is the two elements are combined in a parallel combination. So when you apply force, the force is being applied to both of them. And then, so the force will be accommodated partly by this and partly by this. And therefore, you can write this relation as Fe plus Fv. But the strain in both of these two must be constant, must be same. And therefore, E is equal to EE is equal to EV. Now again, we will do the similar kind of analysis. First, we will assume that a sudden force is applied. At time t equal to 0. So when you apply the force, we know that the dashpot cannot take instantaneous strain, and which means if there is no strain here, there will be no strain on the spring part, and therefore there is no force in the spring, and all the force is being taken by, all the force load is on the dashpot. So initially dashpot carries the whole load. But over time, when there is a constant force on this dashpot, therefore it will deform. And when this will deform, it means there will also be deformation over here. And so there will be some strain over here. And therefore there will be equal strain in both the part. There will, whatever strain happens here, that will be the amount of strain here, and meaning that much force is being now accommodated over here. And if we write it in the differential form, dE is equal to dEE, it will come in handy. And then spring operates. Now, if you look at very, very long time at t equal to infinity, what will happen? If you had applied a stress, then eventually the deformation will take place here, and this deformation will also imply that the spring wheel is getting deformed, and which means that the resistance force is increasing. So at some point this resistance force will be balanced by the external force, and that will mean that there is no more force being carried by the dashpot. So in the final equilibrium condition, all the force would be carried by the spring, and therefore we can calculate the final amount of strain that would be applied. Let's call it E infinity, which is at t equal to infinity. And if the force applied was F, so the total amount of strain that is being applied, that will be there in the system, eventually will be equal to F by KE. But we also know that F d EV by dt is equal to FV by KV. But FV is equal to F minus FE, so we can write it as F minus FE by KV. And if we write it with take it the KE by KV factor out, then what we have here is FE by KE minus E. We can also write KE by KV as 1 over tau. So this is E infinity minus E dE by dt, and therefore this becomes dE by E infinity minus E equal to dt by tau. And then when you integrate, what we get is ln E infinity minus E by E, and there is a minus sign here, so it becomes minus t by tau. And now when we simplify it further, what we get is which is 1 minus, we can take this over this side, and this is 1 minus infinity, so 1 minus E infinity by EE, so we can write it as I just realized I have committed a blunder here. It should have been, after integration, this should be E infinity. Okay, so that is what, when I was writing, I felt there was something wrong. Now it makes sense. So it is 1 minus E by infinity, and therefore when we put it this side, we'll get this form of the equation. And so here, what did we do? We applied sudden force. So this is T equal to 0. This is the force that we applied, and the strain, initially, like we said, that there will be 0 strain, but it will eventually rise to this value E infinity, which is the final strain value. So it will look like this. This is the E infinity, and this is T equal to 0. So and the y-axis strain. So for this condition where we have the two elements in parallel, and if we apply sudden force, then initially the strain is 0 and it eventually grows to E infinity. So this is what we obtain when we look at the mathematical equations. Now the second condition is, what if sudden extension is applied? Now here both spring and dashpot are in parallel. Implies sudden extension of dashpot should also take place. There is no way that you can apply a sudden extension to this whole system and only the spring extends, not the dashpot. But then we know that the dashpot cannot show or display a behavior where you can have sudden extension, which means this type of problem cannot be solved considering this configuration. Therefore, this is a impossible condition. So first let me write, but dashpot cannot have sudden extension, and hence it implies impossible condition. So if you happen to model a particular material, polymer material, using this kind of configuration, then you must also be aware that this kind of system will not accommodate any sudden extension. So this is what we understand from this mathematical formulation by solving this mathematical formulation. Continuing with our simple model, let's look at one more simple model, which is one level higher in terms of complexity than what we have already considered. So what we do here is combined parallel series configuration. Which is also called as Voigt Maxwell model. Now, as the name suggests, what we have here is a configuration where you have both the things. You have the spring and the dashpot in parallel and also in series. So the spring and the dashpot, these two are in parallel, and the dashpot and the spring, these are in series. And we can call it K1, this has K2, and this has KV. So let's say this is where you are applying force, and the basic equations that will govern this response F. So this F will be equal to the sum of this F, which means F is equal to F1 is equal to F2 plus FV. So this is the force in the second spring, and this one is the force in the dashpot, and this is the force in the first spring. So this force is same as the total force that you will apply, and EV is equal to E2 because these two have to be same, and total strain would be equal to E1. It should be E1 plus E2, right? Yeah, so it will be E equal to E1 plus E2. Now let's solve this response for different conditions. So let's assume sudden application of force at time t equal to 0. Now for this, for the dash part, we know dEV by dt is equal to FV by KV, but FV is equal to F minus F2 for the two in the parallel. This is what we get, and F2 is equal to F minus K2 E2 by KV, which is equal to, if we take K2 as common outside, then what we get is K2 by KV F by K2 minus E2, which can also be written as EV. Now for F by K2, we can write F by K2 as the strain, which is equal to E infinity, which will be the total strain minus the instantaneous strain. So F by K2 is a term which implies that total force is acting on this spring, and what will be the elongation at that time. So when we are talking about the total force acting over here, it means it is the condition where the total load is, initially the load was being shared by these two, but now we have the load being only shared by this part. And over here, the strain would be equal to the total strain only when the total force is acting only on this, and therefore there is no strain. Therefore, this is F by K2. Now, this one is equal to, if we assume that the total strain is E infinity, then E infinity minus the strain which was caused by this much, by this spring, which is, let's call it E naught. So if the strain because of the spring constant for the first spring is equal to E naught, therefore F by K2 can be written as E infinity minus E naught. And therefore this makes our task a lot more easier. Now we can again use the method that we applied here earlier. We can write K2 by KV as tau, and therefore what we have here is dt by d tau. And now when we integrate it, what we will have is so we have a variation for the strain in the dashpot, and we know that total strain is equal to EV plus E1, which is same as E naught. Therefore, when we expand it and then add it, then it becomes E infinity minus minus t by tau. And what this means is that we applied a sudden force like this. So this is t equal to 0, this is time. And in response to this, the strain we get is like this, where we have E naught because of the spring 1, and then exponentially reaching this value E infinity, which is primarily due to spring 2. So it is again, if you look at it carefully, it is just sum of the earlier two conclusions. So this one is the series part and this is the parallel part. And we are just getting a sum of these two when we apply a sudden force. Now let's look at the condition where we will be applying the sudden elongation. So let's look at the condition of sudden elongation. And again, if we remember from our earlier discussions that this dashpot is not in a position to take sudden elongation. So it means when you apply a sudden elongation, all that strain would be accommodated over here. And with time, which will also mean that there is a force on the dashpot and therefore it will deform, and therefore some amount of strain will get transferred to this, and therefore the force will also get transferred to this, and eventually it will take all the load that has to exist. And again, it would seem like it is just a combination of our earlier results. So all of sudden strain occurs in spring 1. So E, which is the total strain that has been applied, is equal to F by K1. And at time equal to t equal to 0, if we call the force as F naught, then F naught is equal to EK1. Now at time, at very, very large time, at very large time, t tending to infinity, what we will have will be an equilibrium condition where the strain will also be accommodated by spring 2 and the load will also be accommodated by spring 2, which will equal to the total force that we will be applying at that particular point of time. Therefore, E would be equal to F by, which will be the same force for both the conditions, F by K1 plus F by K2, or in other words, if we call it F infinity, then it is K1 plus K2 by K1 K2, or F infinity would be equal to K1 K2 by K1 plus K2 times E. So this does not reduce to 0. That is one important thing that we need to realize over here. And there is an initial force which will is equal to EK1, and eventually it reduces to this value F infinity. And how it reduces, this one we will not derive. I will just directly write the equation. This will be equal to F naught minus so T sigma, tau sigma is basically the stress relaxation time. and this stress relaxation time is given by Kv by K1 plus K2. So the F force reduces from F0 to this particular value with time when we apply a sudden elongation. This is what we obtain from the mathematical description for this condition. So we have not gotten too complex here, but we see that the formulations are getting more and more tough. But that is still tractable problem. We can still solve it. And we can get an equation, explicit equation for the variation in strain or variation in force. Now to sum it up, let's quickly solve one simple quick problem which will give us some idea about the relation between K1 and K2. So it is given that F0, which is for this particular condition, F0 by infinity is equal to 1.02 by 1.02, and you are asked to find tau E, which is the strain relaxation time, by the stress relaxation time. Now, if you go back and look at the relation, you would see that tau E by tau sigma will come out to K1 plus K2 by K2. And you would also find that E is equal to F0 by K1. So this is the initial force, which is also, and the total strain is also equal to, because it is constant, is equal to 1 by and therefore F0 by F infinity is equal to K1 plus K2 by K2, which means it is same as tau E by tau sigma, which is equal to 1.02. Okay, so this is our understanding for viscoelasticity. We have looked at the mathematical formulation for viscoelasticity, and for different models, different simplified conditions, and we also solved the variation or the response of the material in terms of force variation or the strain variation for two different conditions. One, whether you are applying sudden force, or other where you are applying sudden strain, and we were able to obtain a relation for this. So with that, we end this topic on viscoelasticity, and next we will start discussing about plastic deformation. Thank you.